Hello everyone, and welcome to the fifth topic in the SS3 Physics first term curriculum. Now, in our last class, we were able to consider what happens when you have different types of cells. We talked about the primary cells, we talked about the secondary cells, the types of cells that we have for primary, examples of primary cells, examples of secondary cells, amongst the others. And one of the things we did mention in that discussion was we talked about something called electrolyte, which actually leads us to what we have in this topic. Now, the topic itself is known as conduction of electricity through liquids and gases. In other words, conduction of electricity in fluids, right? And what we are going to be looking at majorly here is known as electrolysis. So as part of this topic, I will be looking at the meaning of electrolysis, and then there we'll define what electrolysis is. We are also going to define what electrolytes are. The different types of electrolytes that we also have will be mentioned at that section. After that, we then look at the dynamics of charged particles, otherwise known as ions. We look at their dynamics, that is how they move during electrolysis. After that, we look at example of electrolysis, where we mention different electrolysis and what happens in each of these types of electrolysis. And then we look at the applications of electrolysis. There are some applications of electrolysis that we see around us but do not know. We mention them, and then you begin to appreciate the beauty of electrolysis and how it helps human endeavors. After that, we look at the Faraday's laws of electrolysis. At this point, there are two laws we're going to consider, the two Faraday's laws of electrolysis, and then we're going to apply them to solve problems on electrolysis. We'll be taking some questions from the WAEC exams, from the JAMB exams, and so on. And then I'll be giving you some tips at that point as to what to do whenever you face a specific type of question under electrolysis. Then once we've done that, we'll have completed conduction of electricity through liquids, and then we go to conduction of electricity through gases. I will look at what it means, and then we look at the conditions necessary for a gas to be able to conduct electricity. Okay. After that, we then look at what is known as thermionic emission. Now, these are the different aspects we're going to consider under the topic conduction of electricity through fluids. Don't forget our main focus here is electrolysis. Okay, now if you are seeing this video for the first time, this is Oya Learn. We are your flawless school too, where we give you very good academic videos that help you grow. The kind of videos that when you follow, you become the top in your classes. So if you have that goal to always ace your academic endeavors, this should be your channel. So ensure that you are subscribed to the channel. You can do this by clicking the subscribe button, and then ensure that you also interact with our videos by dropping a comment or liking the video, and help us to reach many more students like you who need the kind of helpful content that we create right here on Oya Learn by sharing the video. Thank you so much for that. Now, if you're ready, let's look at electrolysis in more details. To understand electrolysis, Michael Faraday, the founding father of what we know as electrolysis, conducted several experiments and then built up the theory that we now know as electrolysis. You see, some liquids are able to conduct electricity because there's a chemical change that go on in them, which splits them into different types of ions, the positive and the negative ion, and as such it makes it possible for them to carry electric current. Okay, now this process whereby a particular liquid is able to conduct electricity is known as electrolysis, and we are defining it according to how Michael Faraday has laid the foundation. We will say that electrolysis is a chemical change, that is a chemical reaction that occurred in a liquid due to the flow of electric current through the liquid. That is, the moment electric current is passed through the liquid, it goes through this chemical change which enables it to continue to carry current. Now, that itself is known as electrolysis. And as I've mentioned, some liquids are able to carry electric current while some are unable to do that. Now, there's this common experiment that is usually done where you connect a light bulb or an LED to a set of cells or batteries. And then when you try to connect the circuit through water, now if the water is pure and then you put the different terminals of the circuit into the water, you discover that it is unable to carry electric current sufficiently and the light bulb does not come on. Now, when you add a little bit of salt into that same water and then stir, after a few seconds, you see that the light bulb comes on, which means that some chemical changes has gone on in the water at the addition of that salt, which enables the new solution, which is now salt solution, to carry electric current, which again goes to prove that pure water is unable to carry electric current, but salt solution is able to do that. This gives us different types of liquids, the types that are able to carry electric current and the types that are unable to carry electric current. Now, liquids that can carry electric current are known as electrolytes. Let's put that down. Liquids capable of conducting electricity are called electrolytes. Now, to give you a few examples of these, we have examples such as acids. Acids are able to carry electricity. I talk about sulfuric acid and the like. Remember when we were talking about cells earlier, we did mention that there are some cells whose electrolyte is sulfuric acid, dilute sulfuric acid in some cases, okay? Now that tells you that acids are able to carry electric current. This is because it's a polar solution, okay? We also have bases. Bases are also able to carry electric current, and then salt solutions. These three are examples of good conductors of electricity, that is good electrolytes. Now, liquids that are unable to carry electric current or conduct electricity are known as non-electrolytes, with examples such as paraffin or kerosene, okay, being a sample or an example of non-electrolytes. So let's write that down. Liquids not capable of conducting electricity are called non-electrolytes, e.g. paraffin or kerosene. This is an example of a non-electrolyte. Now, to recap this, I will see that electrolysis itself is a chemical change in a liquid due to the flow of electric current in that liquid. And then if a liquid is able to conduct electricity, such liquid is known as an electrolyte, with examples such as acid, bases, and salt solution. And then when a liquid is unable to conduct electricity, non-polar liquids especially are unable to do this. They are called non-electrolytes, and an example of such is paraffin or kerosene. Now, mind you, we do have polar solutions that are unable to sufficiently carry current. Now, there's a difference between being able to carry a ample amount of current and being able to carry just a little amount or unable to carry at all. There's a lot of difference between that. So like when I mentioned pure water itself, it's a polar solution because it can dissociate into hydrogen ion and hydroxyl ion, which is positive and negative ions. However, it is unable to sufficiently carry electric current, so which makes it a very weak electrolyte. So that is, you can have strong electrolytes and weak electrolytes, okay? But non-polar solutions are typically non-electrolytes. So with examples such as the kerosene. Let me give you another example. Benzene. Benzene is also a non-electrolyte. Okay, so this is what electrolysis means. and electrolytes and non-electrolytes with examples have also been stated. Don't forget that if you do have any question, drop it in the comment section and we'll attend to all of your questions. So now that we can define electrolysis, let us take a closer look at electrolytes and electrodes. And because as we talk about electrolysis, as we discuss it, as we give examples and all this, and these are some of the terms that we would mention loosely. Terms such as electrolytes, terms such as electrodes. So as a student, you should be able to define each of these terminologies and be able to explain what they do. So let's start with electrolytes. As I've mentioned, some liquids are able to conduct electricity, and these liquids are known as electrolytes. Okay, but to define it properly, we'll say it is a material that is either in liquid or molten form and is capable of conducting electricity. So don't forget, the clues that you have to mention there is that 1, it is a material that is either in liquid form or in molten form. And then the second clue is that it is capable of conducting electricity. That is what makes up an electrolyte. Okay, we've given examples such as acids, bases, and salt solution as examples of electrolytes. And then when it comes to electrodes, right, these are materials through which current enters and leaves an electrolyte. You see that in this definition we make use of electrolytes. Okay, the word electrolyte is in the definition of electrodes. Now, any material at all through which a current enters or leaves an electrolyte is known as an electrode. And there are 2 main types of electrodes which we're going to discuss. But before then, let us put down the definition for electrolytes and electrodes. Electrolyte is any material in liquid or molten state capable of conducting electricity. So this is how we define an electrolyte. Once again, electrolyte is any material in liquid state or molten state capable of conducting electricity. That's an electrolyte. Now, when it comes to electrode, an electrode is any material in form of rod or plate through which current, that is electric current in this case, enters and leaves an electrolyte. These 2 definitions are very important in our study of electrolysis. Like I mentioned, there are terminologies that we will always refer to. And when we make use of terminologies like this, at the back of your mind, you should be able to tell what the meaning of these terminologies are. Because we'll be using these terms loosely as we go in our study of electrolysis, and a good understanding of this will help you understand whatever we say at each stage where we mention any of these 2 terminologies. So once again, an electrolyte is any material in liquid or molten state that is capable of conducting electricity. And then an electrode is any material in form of rod or plate through which current enters and leaves an electrolyte. So that tells you that an electrode can be like a rod, or it can be in form of a rectangular plate, square plate. It could be thick, it could be very narrow. It doesn't really matter. It's just describing the form it comes in, whether it is a rod form or it is a plate form. And it is that electrode from which a current can enter an electrolyte, and from the next electrode it leaves the electrolyte. Remember, it's a flow of charged particles that is known as current. Flow of charged particles. So it is flowing. The current is a flow of charged particles. So the current, the charged particles are moving into the electrolyte from one of the electrodes and out of the electrolyte from the other electrodes. So that tells you there are two electrodes. Okay, so we have what we call the positive electrode. Another name for this is anode. Now, this is where current enters an electrolyte. So let's put that down. Current enters the electrolyte through the anode. Okay, you see these points that we are mentioning here are some of those areas where you get questions, especially in the multiple choice corner, especially in exams such as the JAMB exams and the WAEC, the NAPTEP and the likes. You see some MCQ questions, multiple choice questions, are where they refer to these particular tips that are mentioned here. Don't forget, when we mention the positive electrode, another name for that is what? Anode. So if you're asked, the positive electrode in electrolysis is known as what? The answer to that will be what? Anode. And then what is the function of an anode? You say that current enters the electrolyte through the anode. That leaves us with just one more electrode to discuss. So this is the negative electrode. Now, the negative electrode is known as cathode. Okay, and current leaves the electrolyte through the cathode. Now, note this. Depending on the electrolysis, the cathode and anode can be made of different type of materials. In some particular electrolysis, your cathode or anode can be a different metal from the type of metals you'll be using in a different type of electrolysis. And based on the applications you are trying to get from that particular electrolysis, it changes what you use as cathode and anode like that. So there are some electrolysis where you're trying to electroplate a particular material to have it have a gold plating or a silver plating, all those kind of things like that. When we get to applications, you understand that even better. Okay, so depending on what you're trying to coat in that kind of scenario, it will determine the electrode that you'll be using in that particular electrolysis. So you see that in electrolysis, the cathode and anode are constantly changing. But one thing remains is that the cathode is where current will be leaving the electrolyte, while the anode is where the current enters into the electrolyte. So to recap all of this, do not forget, when you're asked to define an electrolyte, you should mention that it is any material at all that is either liquid or in molten state and is capable of conducting electricity, that is capable of conducting electric currents. And then when it comes to defining an electrode, we say it is any material in form of either a rod or a plate through which current enters and leaves the electrolyte. And as far as electrodes go, we have what is known as the anode and the cathode. The anode is where the current enters the electrolyte, while the cathode is where the current leaves the electrolyte. Let us consider the dynamics of charged particles, otherwise known as ions, in electrolytes. Now, I'll be breaking this down step by step so that you understand every stage of the movement of charged particles in electrolytes. Now, when you have an electrolyte, now remember I did mention earlier in this video that electrolytes are polar solutions. So that means that they have the positive charged particles and they also have the negative charged particles. Now, these electrolytes split into their different charged particles, the positive and the negative, through a process known as electrolytic dissociation. So let's put that down. electrolytic dissociation. Now, this is a process where the charged particles in an electrolyte split. Okay? This is a process where the charged particles in an electrolyte split to give positive and negatively charged particles. So initially, these particles are fused together. Okay, so when electrolytic dissociation occurs, they split. The positive and the negative charged particles now are contained in the electrolytes. Okay, now at this point, they move about randomly. The ions move randomly in the electrolytes. Okay, now what this process looks like is this. So we have electrolyte, okay, where you have your positive, negative, positive, negative, and so on like that. All of them are moving randomly in the solution. Okay, this is what happens at this stage. Now, by the time you then connect it to a potential difference source, such that we have the electrolyte still containing the charged particles like this, and then you place electrodes. I believe you still remember what electrodes are, right? Now the electrodes are connected such that we have cell. Let's put a key, and then let's put a rheostat. Like this. Okay, now this, let's call this the anode, which is positively charged, and let's call this the negatively charged electrode, which is known as the cathode. Okay, by the time you then connect it like this, by the time you allow current to flow, that is, you connect the circuit by putting in the key, you close the circuit. Now current will begin to enter through the anode and leave the electrolyte through the cathode. But what will happen at this stage? When potential difference is connected across the electrodes, the negative ions drift to the positive electrode, while positive ions drift to the negative electrode. And it is by this drifting of ions that the electrolyte is able to conduct electricity. Now, let's break it down one more time. Don't forget that the electrolyte itself contains the positive and negative ions fused, and then after electrolysis, electrolytic dissociation has occurred, and this particle splits. That is, we have the positive particles, that is positive ions split, and then the negative ions are also split. But these ions move randomly in the electrolyte. Now, by the time you connect a potential difference across the electrodes, and that is, the anode is connected to the positive terminal of a battery while the cathode is connected to the negative terminal of a battery. Electrolysis begins. And at this stage, what will happen is that you see that the negative ions will then drift towards the anode, while the positive ions will drift towards the cathode. And as this drifting occurs, they carry charge along with them, so that will make electric current to continue to flow through the electrolyte. And that is the dynamics of ions in electrolytes. Let us now consider different examples of electrolysis. And the first one we're going to look at here is known as the electrolysis of acidified water. Electrolysis of acidified water. For this particular electrolysis, we use what is known as the Hofmann's voltameter. The Hofmann's voltameter. And this consists of two identical graduated tubes. As you can see, we have these two tubes here. They are identical and they have the same kind of graduations, that is measurement markings on them, right? And then they are connected to this funnel through which the acidified water is put into the apparatus. Now, the electrolyte in this electrolysis, the electrolyte is water with few drops of sulfuric acid, H2SO4. Okay, so this is why it is called acidified water. And the reason why sulfuric acid is added to the water is so that it can make it more conducting. Now, I did mention something at the beginning of the video, that water is a polar solution, okay, which means it is capable of dissociating into positive and negative ions. However, it's not a very good conductor of electricity. So in order to make water a little bit more conducting, you can add another solution to it that makes it more conducting. So in this case, what is added is sulfuric acid, just a few drops to make it more conducting, okay? And that is why we call the electrolyte here acidified water. So now that we've gotten the electrolyte, let's not forget that in electrolysis we also use electrodes. Now the electrodes is a pair of platinum plates. Now the plates are located at the bottom of the tubes here. So we have the positive plate here and the negative plate here. They are both platinum. Okay, so and don't forget, the positive plate means what? The anode. Okay, and then the negative plate is what? The cathode. And when we talked about electrolysis earlier, we did mention, especially when it comes to the dynamics of ions in electrolysis, remember that the negative ions will go through through the anode, and then the positive ions will fuse with the cathode. Okay, and don't forget that the current moves into the electrolyte from the anode and out of the electrolyte through the cathode. So all of this also happens in the electrolysis of acidified water. Now, the moment you close these tabs and connect the circuit, something happens here. The water itself will dissociate. Now, water dissociates to give you, remember, H2O, right? To give you hydrogen ion and hydroxyl ion. Okay? Now, when this happens, what you will observe is that you start seeing some bubbles forming around the electrodes. Okay? And as that happens, okay, the bubbles will rise and come to the top of this tube here. But what you will see here is that at this other tube here, less amount of bubble is formed as compared to this. And the bubbles form in the ratio of 2 to 1. Are you with me now? So when this happens, 2:1, that is, you're going to be having hydrogen bubbles here. Because remember, hydrogen is what? positively charged. And what happens to the positive charges in electrolysis? They come to what? The negative electrode, which is the cathode. And more of it comes to this point, and that will give rise to more bubbles at this point. Okay? Then, of course, the hydroxyl comes to this part. But the bubbles you are going to see here is oxygen bubbles. Okay? And here you have what? Hydrogen bubbles. Okay? And don't forget, they are in the ratio of what? 2 to 1. You can tell this by the graduation. Okay? That's why you see when I put the bubbles here, you see that this rises to this marking here, but this is only to this marking. So for just one length of this graduation, we have 2 of it on this other side to show you that is what? 2:1. More hydrogen bubbles than oxygen bubbles. Now, this is not limited to just the water dissociating. The acid itself is also going to dissociate, meaning that H2SO4 will then give you what? 2 hydrogen ion plus SO4 2 minus. Okay? So this is the dissociations that take place here. Now, as this happens, the hydrogen ion goes to the cathode and then they are discharged at that point. The hydroxyl ion, remember this has hydrogen, this has hydrogen. So more hydrogen is coming, so they discharge at the cathode. But when the hydroxyl and the sulfuric part here come to the anode and are discharged, please take note, at this point, the hydroxyl would discharge more than the sulfuric part. Okay, we have more hydroxyl discharging at the sulfuric part, and this would give rise to the production of oxygen and water. And this is what the chemical equation for that particular reaction, this is what it looks like. You're going to be having something that looks like this: 4 hydroxyl. Okay, remember it's the hydroxyl now that is discharging, right? And remember, hydroxyl is what? Negatively charged. Okay, and now this is going to give rise to what? The product. The product is going to be what? Oxygen, water. Okay, and because it is electrolysis, you will also have electrons. So these are the chemical equations that represent what happens in the electrolysis of acidified water. Let me quickly recap so that you do not forget any important detail in the electrolysis of acidified water. First off, you know that what you are using, the apparatus, is what? Hofmann's voltameter, which consists of what? Identical tubes with a funnel attached through which the electrolyte is poured into the apparatus. And the electrolyte used here is what? Acidified water. That is water with a few drops of sulfuric acid. And the purpose of the sulfuric there is to make water more conducting. Okay? And then the electrode is a pair of platinum plates. So we have 2 platinum plates to serve as the anode and the cathode. And then as electrolysis begins, when you close the tabs and then connect the circuits, and you're going to say formation of bubbles, which is due to what happens in electrolytes, the dynamics of ions in electrolytes. When the negatively charged particles come to the anode and the positively charged particles come to the cathode, based on these reactions you see here, the equations you see here, we have more of hydrogen. So that is why you see the hydrogen bubbles will form more than the oxygen bubbles, which is produced to 2:1. The ratio there is 2 to 1. So for every hydrogen bubble that forms, 2 hydrogen bubbles will be formed in the what? The cathode tube. This is the anode tube. This is the cathode tube. And because of this reaction that we see here, there is production of oxygen, water, and electrons. And that's the explanation of the electrolysis of acidified water. The next example of electrolysis we're going to consider now is the electrolysis of copper sulfate solution. Now, in this electrolysis, 2 copper electrodes are immersed into a copper sulfate solution, and then current is passed through them. Okay, so what this means is that the electrolyte the electrolyte is copper sulfate solution. Copper sulfate solution. And you know that copper sulfate solution is when you mix CuSO4 and water. Okay, now this is the electrolyte, and for the electrodes, copper plates are used as electrode. That is, the anode and the cathode are both copper plates. Now, when you want to do this electrolysis, you can take the concentration of the copper sulfate solution and then the mass, measure the mass of the copper electrodes that are used, both the anode and the cathode. Now, this is what you're going to see that happens during the electrolysis. You see that by the time you connect the circuit, right, you will begin to see something occur. After about 30 minutes of allowing current to pass through the electrolyte, you will see that a fresh coating of copper will appear on the cathode, right? While the anode will now look duller than it was before the electrolysis occurred, before the electrolysis process at all. Okay? And if you should measure the mass of the anode and the cathode after electrolysis, you will see that the anode would have lost some mass while the cathode would have gained some mass. And the amount of mass gained by the cathode is equal to the amount of mass that is lost by the anode. However, the concentration of the electrolyte is going to remain the same no matter how long the electrolysis took place. Okay, now this is why it happened. You see, when you have copper sulfate solution, right, when electrolytic dissociation occurs, the copper sulfate is going to split. You're going to have copper sulfate becoming copper ion and SO4 2 minus. Okay, so when you have this occur, remember the water too will dissociate. Don't forget that when we say something is a solution, it means it is in liquid form, it has been dissolved in water. Okay, so and you would have hydrogen ion plus hydroxyl ion. Now, what happens at this stage? Don't forget that in electrolysis, the positive ions are going to be discharged at the cathode. That is, they will drift towards the negative electrode, while the negative ions will drift to the positive electrode, which is the anode. Okay, now copper takes precedence over hydrogen in this electrolysis. Okay, so as a result, copper is discharged more at the cathode. This is the reason why you see that the cathode is going to take a fresh coating of copper, right? Now, at the anode, at this point here, we have SO4 2 minus and hydroxyl minus, which will be discharged at the anode. Okay, now at the anode part here, what takes precedence is copper, and then you see copper itself, okay, giving you Cu2 plus and then electron. So this is the reason why you see that you are having a fresh coat of copper on the cathode while the anode is going to appear dull. So this is all that takes place during the electrolysis of copper sulfate solution. Now, things you shouldn't forget is that the electrolyte is copper sulfate solution. The electrodes are copper plates, okay? And after the electrolysis, the cathode will gain more mass because you now see an appearance of a fresh coating of copper on it, and that mass gained is equal to the mass lost by the anode, which you will see by the anode appearing duller than it was before the electrolysis. And these are the equations that describe what happens during the electrolysis of copper sulfate solution. Finally, on example of electrolysis, let us look at the electrolysis of copper sulfate solution with platinum electrodes. And just like the name suggests, in this case, the electrolyte is copper sulfate solution. Electrolyte is copper sulfate solution. That is CuSO4 and H2O. Okay? And the electrodes are platinum rods. Now, what you are going to observe in the electrolysis of copper solution with platinum electrodes is that when you connect the circuit for a certain amount of time, now you begin to see a bright red coloration on the platinum rods. That is, they become red, bright red as the electrolysis continues. And another thing you will see is that the blue color of the copper sulfate solution becomes paler, right? That is, it loses its concentration. Now, why this occurs is due to the following chemical equations. Now, let's not forget that the copper sulfate would dissociate to give you copper ion and SO4 2 minus, while the water would dissociate to give you hydrogen ion plus hydroxyl ion. Now, what happens here? You see that the positive ions here would drift towards the anode, one of the platinum rods that is being used here. This will drift to it, while at the cathode, this will drift to the cathode, while this, the SO4 2 minus and the hydroxyl ion will drift towards the anode. The negative ions to the anode, the positive ions to the cathode. Now, as a result, because copper takes precedence over hydrogen, you see that it is going to be discharged at the cathode, which will give the cathode its bright red coloration. Okay? And the copper sulfate solution itself would begin to lose its concentration as a result of this dissociation. But that's not the only thing that happens. You see, at the anode, due to the hydroxyl ion there, you're going to see formation of oxygen and water at the anode. That is, you're going to be having the 4-hydroxyl ion to give you oxygen and water and electrons. Okay, so this happens at the anode. So the result of the electrolysis of copper sulfate solution with platinum electrode is the plating of one of the platinum rods with copper. That is why it appears bright red. Another result is the reduction in concentration of the copper sulfate solution. That is, the electrolyte loses its concentration. And then finally, the production of oxygen and water at the anode. Those are the results of the electrolysis of copper sulfate solution with platinum electrode. Now, at this point, if you're yet to be subscribed to the channel, please kindly take a moment of your time, click the subscribe button. Trust me, you do not want to miss the amazing contents that we are giving you right here on Oya Learn, your flawless school too. Ensure that you are subscribed and do engage with the videos by dropping a like and writing a comment in the comment sections of the video. And your comments could contain questions that you have concerning any of the work we are doing presently, especially if you have any area that you would like us to enlighten you or make easier for you. Drop them in the comment section. We promise to attend to all of your comments. And please help us to reach many more students like you by sharing the video. At this point now, we have looked at the different examples of electrolysis. Now let us go to the application of electrolysis. Under the applications of electrolysis, we're going to consider two main applications. The first one is electroplating. Now, electroplating is a process where a metal is coated with a different metal. That is, when you conduct electrolysis with the aim of coating a metal with a different metal in order to either improve its appearance or improve on its property. Like for example, when it comes to electroplating of spoons with silver, silver spoons are produced through electroplating, where silver is coated onto a spoon. Now the spoon itself is a metal. Now you apply a fresh coat of silver on the metal through the electrolysis process, and that is done to improve the appearance of the spoon. Now the same thing could be said of handlebars of bicycles and the likes, that is electroplated with chromium. Now in this particular electrolysis, chromium is going to be coated onto the metal, the iron material that the handlebar is made of, in order to stop it from what? From rusting. Remember that metals corrode, they rust as water and precipitation drops on it. So if you want to stop that particular metal from rusting, you can apply fresh coat of chromium, which is a particular metal that does not corrode. So as a result, when you do electrolysis of the handlebars with chromium, you are reducing the process that could lead to corrosion of such metals. So you are preventing it from corroding or rusting. So let us put the important facts of electroplating down. Let's not forget that first, the electroplating, this is a process where a metal is coated on the surface of another metal in order to improve its appearance or property. Now, when it comes to appearance, it's either you are giving it more luster, that is more shine. You want it to, blink, look shiny, look expensive, and all of that. And then in the case of property, either you are trying to stop it from corroding or rusting and the likes. Okay, so whenever you coat a metal with a fresh metal, a different type of metal entirely, either to improve the appearance or property, what you're doing there is electroplating. It's one of the applications of electrolysis. Now, when you are electroplating a material, these are what you require. Number one, materials for electroplating. The first thing you need is the electroplating material. Now, this is at the cathode, at the anode, I mean. This is at the anode of the voltameter. Okay? So like for example, if you want to coat a spoon with silver, right, to improve its appearance, you're going to put a silver rod at the anode. That's the electroplating material. Okay, you want silver to be coated on the spoon, so silver rod has to be put at the anode of the voltameter. Now, the second thing you need is material to be electroplated. Now, this is at the cathode. So that is the spoon now that you want to be electroplated, that you want to coat with silver is going to be what you use as your cathode. The negative electrode will be the material you want to electroplate, while the positive electrode is the material that you want to wear off, so that you can add that particular property of that material to the one that is placed at the cathode. So electroplating a spoon to make it silver will imply that you use silver as the anode and the spoon as the cathode. And for the third and final thing you require for electroplating of a material is an electrolyte, which is the salt solution of the electroplating metal. So when it comes to electroplating of a spoon now, you want to electroplate it with silver. Your anode is silver rod. Okay, the cathode is the spoon that you want to electroplate, while the electrolyte is potassium silver cyanide, which is a salt of silver. So it's a silver salt solution that has to be used as the electrolyte, and the spoon you want to electroplate becomes your cathode, while a fresh silver rod is the anode. And if you conduct the experiment, at the end of electrolysis, you discover that the silver rod would have lost some mass, right? And the mass lost is going to be the mass that will be gained by the silver spoon. And that's just the explanation of electroplating. There are other materials that could be used for electroplating process. Aside from silver, you could also use chromium, like I mentioned in the case of the handlebars of bicycles. You can also use nickel. You can also use gold, amongst other metals that are used in the process of electroplating. The second application of electrolysis is seen in the calibration of an ammeter. Now, what this means is that you're trying to ensure that a particular ammeter is set or calibrated to measure current accurately. Should I use the word precisely in this case? You want to make sure that it takes precise measurement of electric current. Now, the electrolysis you can use here to calibrate an ammeter is like an example of such is the electrolysis of copper sulfate solution using copper electrodes. Now, let's not forget that in that particular electrolysis, you have a copper sulfate solution, and then you have your electrodes, which are copper electrodes. Okay, now let's call this the anode, and this the cathode. Now let's connect it. We're going to be having a rheostat will be connected at this point, and you can place your key here. Okay, now this is what the circuit itself looks like, and inside here, of course, we're going to be having copper sulfate as the electrolyte. Okay, this is copper sulfate solution. Okay, now at this point here, we can place the ammeter to be calibrated. Now, what happens is this. The moment you connect this circuit, currents begin to flow because the copper sulfate will dissociate, of course, to give you copper ion and SO42 minus. The water will also do the same thing, where you have hydrogen ion and hydroxyl ion. And as we mentioned, is that what you will see here is that this copper that is at the cathode will now have a fresh coat of copper on it. That is, this one will appear duller, while this one will appear brighter. showing that copper has been taken away from, some surface copper has been taken away from this anode, and that has been deposited onto the cathode. Now, before you begin this process, you have to make sure that you measure the cathode before you apply potential difference. This particular cathode, you measure the mass. Now, after you have then began the experiment, one thing you have to ensure is that you continue to make sure that the current passing through this entire system remains steady. So that is, you do that by varying your rheostat, of course. So if the current is rising, you drop it. If it is dropping, you increase it by shifting the rheostat to just make sure that the current that is passing through this system for the amount of time you want to conduct the experiment remains steady. So if you want to use 1 ampere of current, you use 1 ampere of current for the total amount of time you are conducting the experiment. So if it is 30 minutes, you make sure that it is that same 1 ampere of current for the entire 30 minutes that you are conducting the electrolysis. Now, of course, after the time, this copper will have a fresh coat. This copper cathode will have a fresh coat of copper on it, so it appears brighter. So what you now do here is you wash it and then take the new mass of the copper cathode. This will enable you to get the mass of copper deposited. Remember, you have taken M1, okay, which is mass of cathode before electrolysis, and then you take M2, which is mass of cathode after electrolysis. Now, what does this give you? You will see that M2 minus M1, let's call this M, and this would give you mass of copper deposited. During electrolysis. You also need the time taken, of course. Remember, you could do it for 30 minutes, you could do it for 1 hour, but ensure that it's the same current that flows throughout the entire time you are conducting the electrolysis. Now, at the end of this, you are now going to do this calculation where you have, remember, there's an equation that says M equals ZIT, where M is mass deposited, Z is the electrochemical equivalent of material or electrode used. Okay, I is current and T is time. Okay, and this time is measured in seconds. So by applying this, you can find the calculated amount of current that should be flowing for that particular mass to be deposited, and that current becomes the mass deposited divided by the electrochemical equivalent of the material, in this case, electrochemical equivalence of copper, and then multiplied by time. Now, when you calculate this, you get the theoretical or the calculated value of current, okay? And that will give you the error in measurement of this particular ammeter. Because this ammeter is going to read a particular amount of current, say we kept it at 1 ampere as I was mentioning here, right? So if after you did the calculation, you are discovering that for that amount of time and based on the amount of copper deposited, it should have read perhaps 0.9 amperes or 1.1 amperes. That difference in the current reading will then help you to calibrate the ammeter so that it can then measure current correctly. So this is how we use electrolysis to calibrate an ammeter. When Michael Faraday conducted experiments passing electric current through liquids known as electrolytes, he made some findings. And these findings are led to 2 statements that he made, and these statements are now known as the Faraday's laws of electrolysis. Let us begin by explaining what the statement says. Now, mind you, these statements are what summarizes what occurs during electrolysis. That is the result of electrolytic process. Now, the first statement, which is known as the Faraday's first law of electrolysis, states that the mass of substance liberated during electrolysis is directly proportional to the quantity of electricity passed through the electrolyte. Now, why he gave this statement is because he saw that as he began to increase the quantity of electricity that is passed through the electrolyte, he saw that the mass of the substance being liberated continued to increase in the same proportion as the increment in the current. Okay, so and the same thing happened when he reduced the electricity. He saw that the mass that is being liberated is also reduced in equal proportion as to the reduction in the electric current. Okay, so this is what forms the basis for the Faraday's first law of electrolysis. Let's write down the law itself. Faraday's first law of electrolysis states that the mass of substance liberated during electrolysis is proportional to the quantity of electricity passed through the electrolytes. Now, if we're going to put this statement mathematically, it means that M is proportional to Q, where Q is the quantity of charge which is measured in coulombs, and N is the mass of the substance that is liberated. Now, we should know from our study of electricity that charge Q is IT, okay, which is current times time. Now, what this means is that the mass liberated is proportional to a product of the current that is passed through the electrolyte multiplied by the time during which the electrolysis took place. Now, every time we remove the proportionality symbol, you always have to introduce a constant. So in this case, M will now equal the constant, which is denoted Z, and then we have IT. Now, what does all of this mean? Remember, M, mass of substance liberated, okay, and then I is current passed, which is measured in amperes, and then T is time taken for electrolysis. So, and this is measured in seconds. And then the Z is known as electrochemical equivalent. Equivalent of the substance. Now, what does electrochemical equivalent of a substance mean? Okay, now electrochemical equivalent of a substance is the mass of that substance that will be liberated per coulomb charge passed through the electrolyte. Okay, so let's put that down. ECE is the mass of substance liberated per coulomb of charge passed. Okay, so that is the amount of the material that is liberated per 1 coulomb of electricity that is passed through the electrolyte gives you the electrochemical equivalent ECE of such material. Now, every material has their own electrochemical equivalent. All of this helps you to be able to solve problems regarding the first law of electrolysis. Now, before we begin to apply this particular equation, M equals ZIT, let us look at what the second statement that forms the Faraday's second law of electrolysis says. And then we can then use either of the two to then solve questions on electrolysis. What led to the statement that Michael Faraday made, which we now know as the second law of electrolysis, the Faraday's second law of electrolysis, arose from when Michael Faraday compared the masses of different substances that are liberated with the same quantity of electricity. That is, when it passed the same amount of current for the same amount of time for the electrolysis of different substances. For example, if we do electrolysis of copper and electrolysis of silver, and you apply the same current for the same timing, you then compare what happened to the masses of copper and the masses of silver that is liberated by those two electrolytic processes. And this is what led to the Faraday's second law of electrolysis, which states as follows. Faraday's second law of electrolysis states that the masses of different substances deposited during electrolysis with equal quantity of charges is proportional to their electrochemical equivalent. Equivalence. Now, what does this mean? It means that when you conduct electrolysis of copper, for example, you will find that the mass of copper deposited equals the electrochemical equivalent of copper multiplied by current and time. Remember, the same current and time is going to be applied in both. So let's call this equation 1. Now, during the electrolysis of silver, you see that the mass of silver deposited will give you the electrochemical equivalent of silver multiplied by the same current and the same time. This is equation 2. Now, from equation 1, okay, we can say that IT is what? MC over ZC. Okay, and from equation 2, the same IT now equals what? Mass of silver over electrochemical equivalence of silver. So since both are the same, we can then say that mass of copper over electrochemical equivalence of copper equals mass of silver over electrochemical equivalence of silver. So you can apply this to electrolysis of different materials and gives rise to the equation M1 over Z1 equals M2 over Z2. 2. This is the equation formed from the Faraday's second law of electrolysis. Now get this right. From the first law, you are only considering the electrolysis of a particular material, and that gives rise to M equals ZIT, right? But in the second law, you are considering electrolysis of different substances applying the same current for the same amount of time. And that is what led to this particular equation. So depending on how a particular question is framed is what will determine which of these two equations from the Faraday's laws of electrolysis that will be applied to get the appropriate solution required of you in such questions. Now, what we're going to do is we'll be looking at different examples of questions that touch each of these laws of electrolysis. And as we solve these problems, I'll be giving you tips, that is, things that you should watch out for that will enable you to understand what the question requires of you, which equation to use, and how to apply it correctly. So please get your materials ready, and don't forget, if you do have any question at all as we go on to solve these problems, do ensure that you drop your questions in the comment section, and we'll definitely attend to all of your comments. And don't forget to subscribe to the channel, like the video, and also share the videos. This question says, find the mass of copper deposited at the cathode of a copper voltmeter if a current of 0.5 amperes is passed through it for 30 minutes. Now, when you want to solve a question like this is the way to go. This question requires the application of the Faraday's first law of electrolysis, which states that M equals ZIT. Don't forget, Z here is the electrochemical equivalent of the material. So since we are dealing with copper, we are given the electrochemical equivalent of copper. So to get the mass of copper deposited, we then say the electrochemical equivalent, which is 3.3 times 10 to the power of negative 4, which is in grams per coulombs, will now be multiplied by the current. The current is 0.5 multiplied by the time. The time for this particular electrolysis is 30 minutes, which ought to be converted into seconds. And that will give you what? 30 times 60. And this is in seconds. Okay, remember, this is in amperes. This is now in seconds. So now that we have this, we now see that the mass would be, now this means we have 3.3 times 10 to the power of negative 4 grams per coulombs multiplied by, now in this bracket, 30 times 60 will give us 1,800 seconds, multiplied by 0.5 amperes, and that will give us 900 coulombs. Okay, so coulombs cancel coulombs. So the mass deposited now becomes 3.3 times 10 to the power of negative 4 grams times 900. This is 0.00033 times 900. And that will give you 0.297 grams. So this is the mass of copper deposited. Now, let me give you a hint at this point. You see, when you're solving questions like this, some questions like this could be given in multiple choice formats of question. And when you look at the options, it will help you know the value to which you are supposed to give your answers. Now, this is in grams. Okay? There are some questions you will find where the electrochemical equivalent of the material may be given in kilograms per coulombs. Okay? In that case, when you are solving for mass, your answer will be in kilograms. But when you look at the options, it will let you know whether you have to leave your answer in kilograms or in grams. This one is a straight question, so we just leave it based on the particular units that we have from our questions. But some multiple choice question will require to leave this in kilograms. Okay, and when you are doing that, you have to convert this by dividing by 1,000, and that will give you 2.97 times 10 to the power of negative 4 in kilograms. You see that now? So always look out for how your answer is to be placed, whether it is to be given in grams or in kilograms. And the same thing applies to when you are asked to find the electrochemical equivalent of a particular material or the current or the time taken. Watch out for the units. Sometimes the time may be asked to be calculated in minutes or in seconds. So when you get your final answer in seconds, you have to convert it to the required unit. Okay? And the same thing to the electrochemical equivalent. Every time you calculate it, okay, if you are given the mass in grams, your answer will be in grams per coulombs. If you are given the mass in kilograms, your answer will be in kilograms per coulombs. So always watch out for the units. I believe you've got that. Here is another question which says that we should calculate the time in minutes required to electroplate an article of area 300 centimeters squared with a layer of copper 0.06 centimeters thick if a constant current of 2 amperes is maintained. And we are to assume the density of copper to be this given value here, 8.8 grams per cm cube, and that 1 coulombs liberate 0.00033 grams of copper. This gives you the electrochemical equivalent of copper, right? Now, this question is slightly tricky. One, we have to find the time in minutes. Remember I mentioned that when you're solving questions like this, always look out for the particular unit that your answer is required to be in. So in this case, we have to work it in minutes. Another thing that we see here is that we are not given the mass that is deposited directly. So we have to find our way around it. Okay, what we have here is that we are given the area, that is the surface area. We are given the thickness as well. Okay, and we are also given the density. So we have to find a way to get mass from all these 3 different parameters that were given from the question. So to solve a question like this, here's what you do. The first thing you want to get is the mass. Okay, now don't forget that density equals mass over volume. Now what this implies is that mass is what? Density multiplied by volume. So we have to start from volume. So to get volume of copper, to get the volume, we're going to do area multiplied by thickness. Now what does this give us? Now the area is what? 300 cm squared times the thickness, which is 0.06 centimeters. Now what does this mean? What we have here is 300 times, this is 6 divided by 100. Okay, and when you multiply this, you can do that with your calculator. It's going to give you 18 centimeter cube as the volume of copper required. So now we have the volume. The density is also given, so we can find mass of copper deposited. Mass of copper will then be, remember, from this, density times volume. So the density is what? 8.8 grams per cm cube. And we're going to multiply this now by the volume. Okay, the volume is what? 18 cm cube. So multiply this and let's see what the answer is. Let's do that up here, okay? We have 18 multiplied by 8.8. What does this give us? 8 times 8 is 64. So 4, carry the 6. 8 times 1 is 8 plus 6. And that would give us 14. Now, 8 times 8 is another 64. 8 times 1 is 8. 8 plus 6 would give us another 14. So let's add this up. Now, this will give you 4 here. This will give us 8 here. This is 5 and this is 1. So 158.4. So 158.4. And of course, cm cube. Per cm cube and cm cube cancels out. So our answer here is in grams. Mass of copper is in what? In grams. So now that we have this, we can then go on to find the time required. Now, to find that time, we're going to use m equals zit. From here, we can say that the time taken becomes mass divided by z and I. Remember, z is electrochemical equivalent and I is the current. So the time taken therefore becomes the mass deposited or mass required 158.4 divided. Now, this will be divided by Z. The Z is given here, which is electrochemical equivalent. We have 0.00033 multiplied by the current. We are told that the steady current of 2 amperes is allowed to flow. So from here, we can see that what we have is 158.4 divided by 0.00066. And this is going to be measured in seconds. Okay? Now, by the time you calculate this, you should end up with 240,000 seconds. But the question itself asks that we find the time in minutes. So in order to find the time in minutes becomes time in seconds, which is 240,000 divided by the amount of seconds that make up 1 minute, which is 60. And when you do this, what do we have? 60 in 240 will give you 4. So 4,000 minutes is the time required in minutes. And this is how you solve this question. So the answer to this question is 4,000 minutes. This question says, a copper and silver voltmeter are connected in series. And at the end of a period of time, 5 grams of copper was deposited. Now we have to calculate the mass of silver deposited at the same time. Given that the chemical equivalent of copper is 31.5 and chemical equivalent of silver is 108. Now, to solve a problem like this, here's what you do. Now, remember from the Faraday's second law of electrolysis, the mass of one of the material divided by the mass of the second equals to chemical equivalent of 1 over chemical equivalent of 2. Of material 2. So when we apply this, it means that we're going to be having, let's say mass of silver is M1. So mass of silver divided by mass of copper. And the mass of copper here is 5.0 grams equals chemical equivalent of silver, which is 108, divided by chemical equivalent of copper, which is 31.5. Okay? Now from here we can now say mass of silver equals, now this comes up, we now have 5.0 grams times 108 divided by 31.5. Now when you apply this with your calculator, you should come up with a solution that is 17.14 grams. So that is the mass of silver that will be deposited by this electrolysis is 17.14 grams. Don't forget, this is because the same current is passed through since they are connected in series. Remember, in series circuit, the same current will flow. And the current is allowed to flow for the same amount of time. This is why the second law of Faraday applies to this question. And the solution is 17.14 grams. Let's solve this jam question on electrolysis. And we are told that the electrochemical equivalent of platinum is 5 times 10 to the power of negative 7 kilograms per coulombs. Now recall when I mentioned that when solving problems, especially MCQ questions, you have to be very careful with the units you are given. Here we see kilograms per coulombs, and all the other questions we've been working with has grams per coulombs. So you see where these units can really change as you solve the problem. And of course, JAMB, the format of their question is multiple choice. So they always change these units. So you have to be on the lookout to identify the units and apply them in your calculations. Okay, so now we have the electrochemical equivalent of platinum, and they are trying to plate out 1 kilogram of platinum by passing a current of 100 amperes. And now we have to find the time, because it said it must be passed through appropriate vessel 4. So that is the time that it will take to plate out 1 kilogram of platinum using 100 amperes of electric current. So let's find the time. This is how you solve it. Now, when you look at the options, we see that the options are in hours. So that is, whatever we get, which will be in seconds, need to be converted to hours as well. So please take note of that. So now let's go on with the calculations. To find the time is going to be the mass divided by electrochemical equivalent times the current passed. Now the mass here is 1 kilogram. And we're going to divide this by electrochemical equivalent, which is 5 times 10 to the power of negative 7 kilograms per coulombs, times, okay, the current, the electric current required here is going to be in what? 100 amperes. Now, when we work with this, what are we going to have? Okay, you see kilograms here, cancel kilograms. Now, when you multiply this, you're going to get 1 divided by, okay, and when you work with this, we have 5 times 10 raised to the power minus 7 times 100. That will give you 5 times 10 to the power of course, this will now be negative 5. Because this is times 10 squared. And of course, 10 squared times 10 raised to the power minus 7, you add the powers. So that's how we arrive at this point. Okay, and your answer here is going to be in seconds. Okay, so the time is going to be 1 divided by this. That should give you 20,000 seconds. So the time is 20,000 seconds, but the options we have are in hours. So we have to convert this into hours. And to do that, we say the time now becomes 20,000 divided by 1 hour. Now, 1 hour would be what? 1 times 60 minutes times 60 seconds. So we have 20,000 divided by 3,600. And our answer now is in hours. Okay? And when you apply this, you find out that the time is going to be 5.55 recurring. So 5 hours. Okay, and the closest option we see here is therefore option A. So you may not get the exact answer, but it has to be an approximate value of the options that you have. So of all the options we have here, the closest to the value that we have calculated here is 5.6 hours. So that means the correct answer to this question is option A. Here is another question from the SSCEs, which says that if the ammeter records a steady current of 1.1 amperes for 30 minutes while the copper deposited is 0.75 grams, calculate the error in the ammeter reading. Now when we say error in a particular reading is the difference from the calculated reading and the experimental reading. So that is, if during the experiment ammeter is recording 1.1, we have to find the calculated amount of current required for this particular electrolysis and then find the difference between them to get the answer to this question. Now here's what you do. We're going to find the current. Current is mass deposited divided by electrochemical equivalent multiplied by time. Now the mass deposited is 0.75. Now we're going to divide that by 0.00033, and then this multiplied by the time, which is 30 minutes. Remember, this has to be taken to seconds, so that will be 30 times 60. Now when you calculate all of this, remember to do the denominator before you then do numerator divided by denominator. This would give you 1.26 recurring. That is 1.26262626262626 like that. Okay. Now the error would then be 1.26 recurring minus 1.1. And this would give us 0.1626 recurring. So 0.162626262626 like that. Okay, and this is the solution to this problem. Now folks, if you're yet to be subscribed to the channel, this would be a good time for you to take a moment and click the subscribe button. And one other thing you can do is to click the notification bell icon. Now what this does is that it always notifies you every time we put out a new content. So by so doing, you will not miss any of the amazing content that comes right here on Oya Learn Your Flawless School 2. And kindly help us to reach many more students like you by clicking the share button so that they too can get this amazing content that we produce right here on our channel and also get better and make their academic journey even more smoother. And don't forget that if you do have any questions at all, whether it's on what we are doing presently or perhaps during your study time, you came across a particular problem that you like some help with, we are always here for you. All you need to do is drop that question in the comment section of any of our videos and we will definitely attend to all of your comments. Now that we know that liquids are able to conduct electricity, let us now go to the conduction of electricity through gases. Now, experiments have been able to show that gases also are able to conduct electricity under specific condition. And this experiment is carried out using what is known as a discharge tube. So that is to test for conduction of electricity in gases, you make use of a discharge tube. Now, a discharge tube itself consists of a glass rod with metal electrodes sealed at each end. Okay, so let's put that down. This consists of a glass rod with metal electrodes sealed at each end. So that is when you have a glass rod with metal electrode at the end, that's the description of what a discharge tube is. Now, when you are conducting experiments with a discharge tube like this and then it contains gases, and then you apply potential difference to the ends of the electrodes, now this is what you observe. Experiments show that at low pressure and high potential difference of about greater than 100 volts. Now, most experiments work with potential difference as high as 200 volts, 210 volts to 1000 volts. It has to be high potential difference and low pressure. Okay, when the pressure is low and potential difference applied is high, you begin to see that the gases in the discharge tube begins to glow. Now, the reason for this glow is because they gain energy with the potential difference that is applied to them. Because as they begin to conduct the electricity, they are gaining energy. They knock off electron at the cathode end of the discharge tube, giving rise to that glow that we see, which proves that gases are able to conduct electricity at low pressure and high potential difference. Now, with this experiment here now, one of the questions that students are often asked is to state the condition necessary for gases to conduct electricity in a discharge tube. Now, the conditions that make this possible is what? Low pressure and high potential difference. Now, what happened here is that the moment you connect the circuit, what will happen is that the gas itself will dissociate to give the positive and the negative ions. And of course, you already know from when we discussed electrolysis that the moment potential differences are applied across, the negative ions are going to drift towards the anode, while the positive ions will drift towards the cathode. Now, not only the negative ions drift there, even free electrons present will also drift towards the anode. Now, as they begin to move like this, the negative ions that are drifting towards the cathode move in that direction. Positive ions drifting towards the anode continue to move like that. And as they hit the metal, right, they begin to emit electrons at the electrodes. As they begin to contact the electrodes, electrons are being knocked off. And this is what we now know as the cathode ray. The glow of these electrons that are being knocked off is called the cathode ray. This is why it's important that once we understand how discharge tube work, we also look at the cathode ray. But the main thing here that we are discussing is to understand that whenever you apply low pressure and high potential difference to a discharge tube, you see a glow in the discharge tube. This is as a result of the gases they are gaining energy because they are able to conduct electricity. And that's the condition necessary for gases to conduct electricity. As you apply potential difference to a discharge tube, the positive ions are going to drift towards the cathode end of the discharge tube. Now, upon getting to the cathode end, they begin to knock off electrons from the metal plates that makes up the cathode electrode of that discharge tube. Now, these electrons that they knock off is a high energy electron known as cathode ray. Now, the cathode ray itself has its own nature and properties. There are about 10 of them. So let's run through the 10 nature and properties of a cathode ray. Now, the first is that they consist of a stream of fast-moving particles of negative electricity or negative charges. And the name for this is electrons. That is, cathode ray is a stream of fast-moving electrons. And don't forget that these electrons are high energy particles. The second one is that they cause glass and other materials such as the zinc sulfide to glow. It gives it this greenish hue. They glow with a greenish kind of color. Kind of like what you see with neon signs, with fluorescent bulbs that have this, there's this green glow that you see in them. It's as a result of cathode rays in them. Now, the third property we'll be looking at here is about the way they travel. Now, when you experiment with cathode rays, you see that they travel in a straight line. The only thing that can cause it to deviate from its path is when you apply either electric or magnetic field along the cathode, the tube of the discharge tube itself, the glass that makes the discharge tube. When you apply the electrical field or magnetic field along it, it may cause it to deviate. But what we see here is that when there is no such application of electrical or magnetic field, they travel along a straight line. And this gives us the fourth property here. They are deflected by electric and magnetic fields. Let me explain this briefly. So if you have your discharge tube like this, okay, the cathode ray ought to move in a straight line, but by the time you apply a magnetic field, the knot here, you see that the electrons are deviated towards the knot of a magnetic field, which again proves that they are charged particles, and since they are electrons, it means they are negatively charged since they are deflected towards the knot. The moment you reverse the pole of the magnet and apply south, they will deviate in the opposite direction of that magnetic field. And the same thing applies when you apply the electrical field. It will drift towards the positive pole of your electric field, right? So they show that they are deflected when you apply electrical or magnetic fields along the discharge tube. Now, the fifth property is that these electrons are capable to ionize gas. This is because they are high energy particles. So whenever they interact with gases, they cause them to be ionized, which means that the gas will then begin to glow because of the high temperature involved there. So when you interact gases with the cathode ray, they cause them to ionize. These are the first properties, the first 5 properties of a cathode ray. Let's look at the next 5 properties. The next 5 properties or nature of a cathode ray as follows. At number 6, we have that they will turn a light paddle wheel in the tube. That is, when a light paddle wheel is placed within the tube, the cathode ray are capable of turning it. Now, what this shows is that they have momentum. That is energy. They do have energy. They are able to cause the paddle wheel to turn due to their momentum. And number 7, we have that they are capable of producing intense heat on objects, which stops them. So whenever an object is applied to stop the flow of the cathode ray, that particular object becomes highly hot. That is, gains temperature as the cathode ray bombard that material. Now, another property here is that they can affect photographic plates. Whenever you use the cathode rays near photographic plates, they cause an effect on the photographic plate. At number 9, we have that they can produce X-rays from high-density metals. That is, whenever you place a high-density metals within a discharge tube, they produce the X-ray. Remember, we talked about X-ray when we talked about the different types of electromagnetic radiations or electromagnetic waves. So these are produced whenever cathode rays interact with high-density metals. And then finally, at number 10, we have that they are highly penetrating, with cathode rays able to penetrate high metals such as the steel plates. They are able to penetrate steel plates. They are able to penetrate aluminum plates, and even gold foil. These are metals that has been proven that cathode rays are able to penetrate, which shows that they have a high penetrating power. And with this, we have the 10 nature and properties of the cathode ray. Now let us study the applications of gas discharge. One of the applications is in what we know as fluorescent tubes, which is used commercially for lighting and also for sign displays. So let's put that down. We have fluorescent tubes used commercially for lighting and display. Now, the way the fluorescent tube works is this. You see, the fluorescent tube itself consists of either mercury vapor or sodium vapor. Right? Now, as the cathode rays are emitted from the cathode end of the fluorescent tube, they begin to interact or bombard the mercury vapor or sodium vapor, depending on which of these vapors is in that particular fluorescent tube. And as the cathode rays begin to bombard the vapor, let's assume now we are working with the mercury vapor. As they bombard the mercury vapor, it gives off UV radiations and starts to glow. Now, the name given to when materials begin to glow when they are bombarded like this is known as fluorescence. That is, they are fluorescing, which is why this is called a fluorescent tube. That is a glowing tube. Now, most of these fluorescent tubes are coated, the interior part of the fluorescent tube are coated with a particular material known as phosphor. Okay, so when this phosphor interacts, when it interacts with the UV that is produced when the cathode ray bombard the mercury vapor, it then gives off the visible light that we now see. Now, remember that when we talked about electromagnetic radiations, we said that the spectrum that is visible to the human eye, that the human eye can accommodate, is known as the visible spectrum. Remember your Revox G from the electromagnetic spectrum itself. Now, by the time the cathode ray itself bombards the mercury vapor, it gives off this UV light, which is not visible to the human eye at this stage, but it glows slightly. Now, that glowing there is what we see as the interaction between the cathode ray and the mercury vapor. And the way we are able to see this is because they begin to interact with the phosphor, which is the interior coat of the fluorescent tube. And then this gives off the light. And it's a type of light that is more efficient compared to the regular filament lamps. So the fluorescent tube is more efficient than filament light because it gives off a bright white light depending on the type of phosphor or the interior coating of that tube. Now, you can change the coating of the tube to change the color that the visible light will come in. Remember that visible light comes in different colors. We have the red, we have the orange, the yellow, the green, the blue, the indigo, the violet, the 7 colors of the rainbow, right? So depending on the type of coating you use, you can get any of this color. But when all of this color come together, it gives off that white glow that we see, and it is very bright when you compare it with the filament lamp. Now, this is just one of the application of the gas discharge. Another application is seen in the neon signs that we see. If you've seen any neon sign at all, that is one of the applications of gas discharge. Let us discuss what happens in a neon display as compared to the fluorescent tube. In the case of a neon sign, which is another application of the gas discharge, it is basically a discharge tube that is now filled with neon gas. So when you evacuate a discharge tube and fill it with neon gas and put it under low pressure, now contains neon gas and put under a pressure of 5 millimeters of mercury. Now, this is a very low pressure. Remember that they are able to conduct electricity when put under low pressure and high potential difference. That condition maintains in this case as well. So whenever you fill a discharge tube with neon gas and put it under this low pressure, it begins to glow with a characteristic color, okay, because of the interaction of the cathode rays with the different electrodes that we have at the end of the discharge tube. It will give off a characteristic color. Now, the color it gives off depends on the gas that is within the discharge tube. So this is why you see that neon signs come in different colors. You are able to make them to have different colors based on the coating that you have on the inside of the discharge tube. So there are some coatings that will give off the red-orange color. There are some coatings that will give off the white colors. There are some coatings that will give you that hue, that greenish hue color. Depending on how you coat the inside of the discharge tube, it will give you different characteristic color. But the main component remains the neon gas, and remember that it is always put at a pressure that is as low as 5 millimeters of mercury. And that's it on the application of gas discharge. We have learned that in a discharge tube, cathode rays or electrons are produced at the cathode end of the discharge tube, and that particular cathode is known as a cold cathode. Now, another way of producing cathode rays or electrons is a process known as the hot cathode process, and that process is generally termed the thermionic emission. Now, when we talk about thermionic emission, it's a process whereby electrons are emitted from the surface of a metal when it is sufficiently heated to a specific temperature. That is, when you begin to heat up a metal surface, when it gets to a particular temperature, it begins to emit electrons, otherwise known as cathode rays, from the surface of such metal. Let's put down the definition here. Thermionic emission is the emission of electrons from the surface of a metal heated to a sufficient temperature. Sufficient temperature. So, other than using the discharge tube to create cathode rays, another ways by which you can produce cathode rays is through this process known as thermionic emission. This was discovered when Thomas Edison performed some experiments using the different metals, passing electricity through them when gases are used to conduct electricity, and then he found that by the time you heat up metals to a sufficient temperature, they emit electrons, and so it is that process itself is called the thermionic emission. When we consider the phenomena known as thermionic emission and liquid vaporization side by side, we begin to see some similarities as well as some differences between these two phenomena. Now, let's start by considering first the similarities between thermionic emission and liquid vaporization. Now, in both of them, we see that heat is involved. That is, you always have to apply heat for thermionic emission to occur, just as you have to apply heat for liquid vaporization to occur. Both of them involve addition of heat on materials. That's the first similarities between thermionic emission and liquid vaporization. The second similarity is that in both cases, you see that there is the phenomena themselves occur at the surface of the material. Now, there's a slight clause to this. When we look at thermionic emission, we see that electrons are being released or emitted from the surface of a metal by the time you heat it to a sufficient enough temperature. Now, in the case of liquid vaporization, as you continue to apply heat to a liquid, it gets to a certain temperature when the liquid itself begins to leave the liquid state and then escape into a gaseous state. Now, all of this happens within the bulk of the liquid, but the escape occurs where? At the surface of the liquid. Now, I remember that most times when we talk about liquid vaporization, especially when you compare it with evaporation, we do mention that evaporation takes place only at the surface, while liquid vaporization takes place within the bulk of the liquid. But you must remember that the escape from liquid state into the gaseous state occurs where? At the surface of the liquid when it gets to the vaporization point. Okay, so at that point where vaporization occurs and at the point where thermionic emission occurs, both of them occur where? At the surface of the materials they are involved in. Another similarity between thermionic emission and liquid vaporization is that in both cases, the rate of thermionic emission and the rate of liquid vaporization increase as the temperature increases. So that is, if you want fast thermionic emission, increase the heat applied. Once you get to this sufficient enough temperature, you can get more electrons being emitted from the surface of the metal by applying even more heat, which will then increase the temperature at the surface of the metal. And the same thing applies to liquid vaporization. The more heat you apply, the faster the rate of liquid vaporization. I remember when we talked about the escape of liquid into the gaseous state, right? We did talk about the relationship between heat and specific heat capacity of materials, right? That tells you that more heat you apply, the more the liquid changes into vapor, or that is, we say, the more the liquid itself vaporizes, right? And it's by a relationship of what? H equals mc theta. That is, as the temperature is increasing, the vaporization rate also increase, just the same way as thermionic emission increases with increase in temperature. Now, finally, on the similarities between thermionic emission and liquid vaporization, we see that both of them involve the release of particles. Now, in the case of thermionic emission, electrons are being released from the surface of the metal. But in the case of liquid vaporization, we see that the liquid itself becomes what? Gases, and they are emitted at the surface of the liquid itself. So both of them involve the release of particles, and as you continue to increase the temperature, it gets to a point where it reaches a level that is known as the saturation point. At that saturation point, the more electrons that are being released from the surface, or the more particles released from the body of the liquid, is similar to the amount of the particles that are returned into the materials themselves. So at this point, as particles are leaving, some are condensing back into the liquid. The same thing with thermionic emission, where electrons are leaving as much as electrons are added to the surface of the metal, and that particular point is known as the saturation point. And these are the similarities between thermionic emission and liquid vaporization. Now let us consider their differences. Now, looking at the differences between thermionic emission and liquid vaporization. Now, of course, the very first difference we're going to consider here is that liquid vaporization involves liquids, while thermionic emission involves metals. So that is, in the case of liquid vaporization, we see water molecules being released from the surface of a liquid. But in the case of thermionic emission, we see that there is emission of electrons on the metal. So when one deals with liquid, the other deals with metal. That's number one differences. Number two difference, which is similar to this, is that in the case of liquid vaporizations, we see that it is water molecule that is released from the surface of the liquid. Water molecule are released from surface of liquid, in vaporization, while electrons are released from metal surfaces in thermionic emission. Okay, so one involved the release of water molecules, while the other involved the release of electrons from the surface of metal. And then the third and final difference between thermionic emission and liquid vaporization is that vaporization occurs at specific temperature. Now, you know what this temperature is called, right? If you're not certain of this, you can always check out our video where we talked about vaporization, and the temperature at which the water molecules is released from the surface of a liquid of water itself is known as the boiling point. That's the temperature where vaporization occurs, the boiling point, right? But in the case of thermionic emission, it may occur at any temperature. So let's note that down. Thermionic emission, on the other hand, occurs at a range of temperature. Now, this is because for thermionic emission to occur, the metal itself has to be heated to a particular temperature. But beyond that temperature, thermionic emission occurs. Remember that the rate at which thermionic emission occurs depends on how hot the metal surface itself heats. But it does not depend on a specific temperature, unlike the case of vaporization, where that liquid itself needs to be heated to its boiling point. So that's one of the difference between thermionic emission and liquid vaporization. Let's recap. The first one is that what liquid vaporization involves what? Liquids, while thermionic emission involves metals. Secondly, water molecules is what is released at the surface of the liquid, while electrons is what is released from the surface of the metals during thermionic emission. And then finally, vaporization occurs at a specific temperature known as the boiling point, while thermionic emission occurs at a range of temperatures. And that's it on the differences between thermionic emission and liquid vaporization. To end our study of electrolysis, we're going to be looking at the application of thermionic emission. Now, there are two main applications of thermionic emission. One of them is seen in the cathode ray oscilloscope. The cathode ray oscilloscope. Now, the cathode ray oscilloscope is a device that is used to study different waveforms, especially the alternating current waveform. Let's put this down. This is a device used to study different waveforms. Especially AC, that is alternating current waveform. Now, when you do this, you can use it to measure, the amplitude of the wave. You can measure the frequency of the wave. You can measure the wavelength and other properties of a wave. Remember that an AC wave comes in the form of a sine wave. Okay, so what you can visualize this particular wave using the cathode ray oscilloscope. It actually consists of an electron gun at one end and a fluorescent screen at the other end, which enables us to be able to visualize the different wave forms that you can see from, especially the AC wave, which is a sine wave. And when you observe the wave, you can then measure the amplitude, the frequency, and wavelength. And then finally, the other application of thermionic emission is seen in diode valves. Now, for diode valves, it's actually a device that allows flow of current in one direction, so it can be used as a rectifier. Now, when it comes to rectifiers is actually a device that converts alternating current to direct current. That is, to convert AC to DC. Now, we're going to take a deeper study into this. I think that will be more of when we're looking at semiconductor physics. But it's important that we do mention this at this stage so that you're familiar with the applications of thermionic emission. So when asked, how is thermionic emission employed, or what are the applications of thermionic emission, mentioned that one of them is seen in the use of what is known as the cathode ray oscilloscope, and then the second one is in the use of diode valves. And with this, we end our study of conduction of electricity through liquids and gases. Now, folks, don't forget that if you're yet to be subscribed to the channel, we implore you to please do so. Just take a moment of your time, click the subscribe button. Another thing that can help you is when you click the notification bell icon, you will always be alerted every time we put out a new video. And this way you will not miss any of the content that we post right here on Oya Learn Your Flawless School 2. And don't forget that we need your help to be able to reach many more students like you who need the helpful videos that we make right here on our channel. And the way you can assist us is to help us by sharing the video so that they too can get access to the amazing content that we produce right here on Oya Learn. And don't forget to encourage them to interact with our videos by dropping a like and dropping a comment. You also can drop a comment whenever you have any challenge at all concerning your studies. If there's any aspect you would like some help with, remember that we are always here for you. All you need to do is put your question in the comment section of any of our videos, and we promise to attend to all of your comments. Thank you so much for being part of the lesson so far. I will continue in the topic 6. I'll be seeing you in that video. Bye for now.